It exists in legend as a blade that could cut through mythology itself. A sword, forged in the fires of an unknown chemistry. So sharp it could slice a falling piece of silk in midair. So strong, it could cleave through the armor of a European knight, and the sword within it, without losing its edge. This is Damascus Steel. For centuries, it was the pinnacle of metallurgy, the most coveted, most feared, and most mysterious weapon on Earth. Crusaders returned from the Holy Land not with treasure, but with terrifying stories of these blades, characterized by a beautiful, zwilling, watery pattern on their surface. They called this pattern damask. We see this pattern everywhere today. On kitchen knives, on hunting gear, on decorative replicas. We call it Damascus. But it is a lie. It is a cosmetic facade, an acid-etched trick on modern steel, designed only to mimic a legend, because the real thing, the genuine, crucible-forged Damascus steel, vanished from history. Around the year 1750, the knowledge simply stopped. The fires went out, the formula was lost, the anvils fell silent. And this is the anomaly. This isn't just a lost recipe, like a forgotten family dish. This is the disappearance of an advanced material science, a technology so sophisticated that it required centuries, and the invention of the scanning electron microscope for us to even begin to understand what we had lost. How did ancient blacksmiths, working with primitive tools, create a material infused with nanotechnology that we, with all our modern science, are still struggling to replicate? This is not a story about a sword. This is a story about a formula, a glitch in the timeline of human innovation, where the ancient world possessed a secret that the modern world is still trying to unlock. When we talk about Damascus Steel, we are, strictly speaking, talking about two things. First, there is the legend. This is the steel of Saladin, the weapon of the Saracens. The accounts from the Crusades are consistent. These blades were supernaturally resilient, while a European broadsword was a brittle piece of iron, prone to shattering or dulling. The Damascus blade had a revolutionary combination of properties. It was incredibly hard, allowing it to hold a razor-sharp edge, but it was also flexible, capable of bending without breaking. Hardness and flexibility are, in metallurgy, almost always mutually exclusive. You sacrifice one to get the other. Yet, these blades possessed both. They were composites of contradictory forces, bound together by that signature damask pattern. The pattern itself became part of the myth. It was described as moire, like watered silk. Some legends claim the smiths would quench the red-hot blades by thrusting them into the bodies of slaves, believing the infusion of human spirit gave the blade its power. Others claimed they were cooled in the north wind, or quenched in dragon's blood. These are, of course, myths designed to protect a trade secret. The second thing we are talking about is the source material. The blades were not actually forged in Damascus, Syria. Damascus was the trade hub, the marketplace where the finished weapons were sold. The steel itself, the raw material, came from thousands of miles away, primarily from India. It arrived in the Middle East as Wootz steel. Wootz was a marvel in its own right. It was a crucible steel. Indian smiths would take iron ore, charcoal, and specific leaves or glasses, and seal them in a small clay crucible. They would heat this crucible in a forge for days, slowly, meticulously, until the iron melted and absorbed a very high amount of carbon, somewhere between 1.5% and 2.5%. This is a carbon content that, by modern standards, should be useless. It's ultra-high carbon. It's cast iron. It should be brittle as glass. But it wasn't. When these Wootz ingots, or cakes, were shipped to the master smiths of Persia and Syria, they were subjected to a secret, painstaking process of forging. The smiths would heat and hammer, again and again. This forging process was not just shaping the blade, it was transforming the material on a microscopic level. The smiths were performing an empirical, almost alchemical form of material science. They were manipulating the very crystal structure of the steel, coaxing out the damask pattern and, with it, the blade's legendary properties. They were the masters of their craft. And then, suddenly, they were gone. The extinction event for Damascus Steel is chillingly precise. Historians note that by the mid-18th century, the quality of the blades began to decline. The patterns became less distinct. The steel grew more brittle. By 1800, the true art was considered dead. Why did a technology, honed over a millennium, simply vanish? In the span of a single generation, the common historical explanation is a simple one. The supply chain broke. The specific iron mines in India that produced the unique ore for Wootz ingots ran dry. As the raw material changed, the formula no longer worked. This theory suggests the smiths themselves were not scientists. They were craftsmen following a rigid tradition. When the ingredients changed, they didn't know why the recipe worked in the first place, so they couldn't adapt it. The magic was in the ore, not in the smith. Other historians point to devastating political disruption, the invasions of Timor, the fall of the Persian Empire, the colonization of India by the British. All of these events shattered the ancient trade routes and scattered the workshops. The knowledge, passed down meticulously from master to apprentice, was broken. A few masters died without passing on the secret, and the chain of knowledge was severed forever. This is the Orthodox glitch, a confluence of resource depletion and societal collapse. A tragic, but understandable, historical footnote. For 2 centuries, that was the accepted answer. The secret of Damascus Steel was lost to the chaos of history, locked away with the pyramids and the Library of Alexandria, a romantic relic of a bygone age. The blades sat in museums, their patterned surfaces silent. We had moved on. We had modern, mass-produced Bessemer steel. We had alloys, stainless steel, titanium. We had no need for Damascus, until we looked closer, and the story we found was not one of history, but of physics. The first attempts to rediscover Damascus steel began almost immediately. In the 19th century, European metallurgists were obsessed. They were convinced the secret lay in the pattern. They believed the damask was the cause of the steel's properties, not a byproduct of them. Michael Faraday, the father of electromagnetism, tried. He spent years alloying steel with different metals, including platinum and silver, trying to replicate the surface pattern. He failed. In Russia, the great metallurgist, Pavel Anosov, tried to place. He heated and cooled blades at different rates, documented different quenching baths, and came incredibly close. He produced blades with excellent patterns and properties, but even he admitted he could not achieve the consistency or legendary quality of the originals. His death in 1851 effectively ended the Russian research. Everyone was chasing the pattern. This visual-first approach continued for over a century. In the 1970 seconds, it was widely believed the damask was the result of carbide banding. This theory, proposed by metallurgists John Wadsworth and Oleg Sherby, was the most plausible, yet they argued that during the slow forging process, the high carbon content in the Wootz steel would precipitate out, forming bands of an incredibly hard iron compound called cementite, or iron carbide. These cementite bands were the hard part of the equation. The flexible part was the softer steel matrix surrounding them. The blade was a microscopic composite, layers of hard cementite woven into a softer, more ductile steel body. The damask pattern we see? That was just the visible evidence of these internal cementite structures, revealed by the final acid etch. It was a brilliant theory. It explained everything: hardness, flexibility, and the pattern. Case closed. Wadsworth and Sherby even forged blades using this method. They produced superplastic, ultra-high carbon steels that mimicked the properties. The world of metallurgy declared the mystery solved. The glitch was just a misunderstanding of carbide banding. But there was a problem, a nagging detail. A man who looked at the blades and didn't stop at the surface. Enter Dr. John D. Verhoeven, a metallurgist at Iowa State University. In the 1980 seconds, Verhoeven was working with a master bladesmith named Alfred Pendray. Pendray was forging his own Wootz ingots based on historical recipes, and Verhoeven was analyzing them. Verhoeven and Pendray followed the Wadsworth-Sherby model. They made ultra-high carbon steel. They forged it. They got the carbide bands. They got the pattern, but the blades were not right. They were good, but they weren't legendary. The cementite bands were brittle. They would shatter or break apart during the forging process. The steel lacked the supernatural resilience of the originals. Verhoeven was a scientist. He didn't trust the modern replicas. He needed to test an original. He acquired several authentic, priceless blades. And he did what no one had dared. He cut them. He placed them under a scanning electron microscope, long pause, and what he found should not have been there. The orthodox theory was that the cementite bands were large structures, but Verhoeven saw something else. Yes, the large bands of cementite were there, just as the theory predicted, but they were only part of the story. The real anomaly was lurking inside those bands. The cementite structures were different. They weren't just solid bands. They were, on a microscopic level, organized, aligned. They showed a level of complex, ordered structure that simple forging could not explain, and crucially, he found that the blades contained tiny, trace-level impurities, specifically vanadium, molybdenum, and chromium. These elements were invisible to the naked eye, and unknown to the ancient smiths. Verhoeven realized the original Indian ore, the lost ingredient, wasn't magical. It was just dirty. It was contaminated with these trace elements, and these trace elements, he theorized, were the key. They were the catalysts. They were acting as seeding agents, allowing the cementite to form in these strange, organized, and incredibly resilient patterns. The mystery was solved. The glitch was trace-level impurities in the Indian ore. Case closed. Again. But science does not sleep. And in the 2000s, another team of researchers, this time in Germany, got their hands on an even more powerful microscope, a transmission electron microscope, DME. They weren't just looking at the surface of the microstructures, they were looking inside them. And the glitch returned. But this time, it wasn't microscopic. It was nanoscopic. In 2006, researchers at Dresden University of Technology, led by Dr. Peter Paufler, analyzed an authentic 17th century Damascus saber. When they focused the transmission electron microscope on the blade, they weren't just looking for cementite bands. They were looking at the very fabric of the steel. Atom by atom. What they found, unbrief, was, by all scientific accounts, impossible. The blade was not just steel, it was, quite literally, infused with nanotechnology. They found carbon nanotubes, millions of perfect, undamaged carbon nanotubes, preserved within the steel, a material discovered by modern science in 1991. A hollow cylinder of carbon atoms, 1 atom thick, a material so strong, it is considered the building block of future technology, a material we are spending billions to manufacture in clean rooms with plasma reactors. And here it was, embedded in a 400-year-old sword. The German team proposed that the cementite bands Verhoeven saw were something even more complex. Cementite nanowires. Incredibly long, thin, and flexible wires of iron carbide, protected and encased by the carbon nanotubes. This wasn't a replacement for Verhoeven's theory. It was an incredible evolution of it. The impurities weren't just seeding bands. They were seeding an entire nanostructure. This was the real secret. This is why the blades were so strong. The cementite nanowires provided the hardness, acting like rebar in concrete. But because they were nanowires, not just brittle chunks, they could bend and flex without breaking. And the carbon nanotubes acted as a protective sheath, preventing the nanowires from dissolving or cracking under the immense stress of forging and impact. The Damascus pattern, the thing everyone had been chasing for 200 years, was just a visual echo, a macroscopic shadow, cast by this incredibly complex, ordered, nanoscopic structure. The ancient smiths were not just smiths. They were, unknowingly, nanotechnologists. The discovery of carbon nanotubes opened a Pandora's box. It answered what Damascus Steel is, but it created an even bigger question. How? Without a clean room, without a plasma reactor, without any concept of atoms or nanotechnology, did medieval smiths create this structure? This is the process glitch, and it remains unsolved. We now believe the key lies in 3 interlocking factors. Factor 1, the material. The dirty Wootz ore from India, the trace impurities, vanadium, molybdenum were the catalysts. Modern science calls them tube-promoting elements. They provided the template, the seed around which the nanotubes and nanowires could form. The depletion of this specific ore was a factor. Factor 2, the temperature. This is the thermal cycling. The smiths had to heat the steel, but not too much. They had to keep it in a sweet spot. A temperature window, modern science, calls the superplastic state. Around 850 degrees Celsius. Too hot. And the nanotubes would dissolve. Too cold. And they wouldn't form. They controlled this for days on end, using only bellows and charcoal. Factor 3, the work, the physical deformation, the hammering. We now believe the repetitive, low-temperature hammering did not just shape the blade. It catalyzed the reaction. The mechanical stress of the hammer blows was the energy source, stimulating the growth of the nanotubes along the stress lines of the steel. The smith was, in effect, weaving nanotechnology with every strike of his hammer. This is the current, best hypothesis. A perfect storm of unique materials, precise temperature control, and specific mechanical work. The smiths had no idea why it worked. They only knew that it worked. They followed the tradition, the ritual, the process passed down from their masters. When one of those 3 legs of the stool, the ore, the temperature, or the hammering technique was broken, the process failed. The nanotubes did not form. The steel was just steel. The glitch wasn't just the loss of an ingredient. It was the loss of a process, an intuitive, empirical mastery of physics that the smiths themselves could not explain. They were masters of an art they did not understand. Today, we understand Damascus Steel better than at any point in history. We have microscopes that can see the atoms. We have theories that model the chemistry. And yet, we struggle to make it consistently. We cannot replicate the effortless mastery of the 12th century smiths. We can make replicas. We can take modern steel, mix in vanadium, create Wootz ingots, and forge them. We can, in a lab, create blades with cementite nanowires and carbon nanotubes. Dr. Verhoeven and Pendray did it. Modern masters have come incredibly close. But we cannot do it with the effortless mastery of the 12th century smiths. Our modern, lab-grown versions are fragile, inconsistent, or require laboratory controls so precise they are commercially unviable. We have the blueprint, but we cannot build the house using the ancient tools, and this leaves us with the final, unsettling question. Was this discovery, pause, a cosmic accident? A 1 in a billion fluke of geology? Where a specific mine in India contained the exact recipe of iron and trace elements, which, when combined with a specific charcoal heating method and a specific hammering technique, accidentally produced nanotechnology? Long pause. Or, is it possible, pause, that these ancient masters knew exactly what they were doing? Not in our language, not in terms of nanotubes or catalysts, but did they possess an intuitive, empirical understanding of material science that was so advanced, so refined, that it operated on a level we have lost? We view history as a linear progression, from bronze to iron, to steel, to silicon, but Damascus Steel is a glitch in that timeline. It is an artifact from the future, found in the past, It proves that knowledge is not a straight line. It can be discovered, perfected, and just as easily, it can be forgotten. The true secret of Damascus Steel isn't the carbon, it's the fragility of human knowledge. We are left admiring a process we can analyze, but cannot intuitively master.